recording, so if I invite you up and you don't want to have your voice recorded, just let me know and I can take you out. Okay, so I'm talking about... Okay, I don't know how... Can you guys see this? I'm going to have to swap back in and out. Okay, I'm just going to go with it, and every now and then I'm going to come check the chat. And if there's anything like important you want me to quickly look, I can see general, I just can't see the stage chat, so you can tell me to look. Okay, so DFAs, I'm talking about DFAs, NFAs, and determinising NFAs. There might be mistakes, so if there is, please mention it. It's going to help everyone. These are the topics I'm going to be talking about. First of all, I want to talk about the problem, because I feel like it's important to know why we're doing automata and what problem it's solving, rather than just understanding how it works, understanding its purpose. Then I'm going to introduce automata through DFAs, because I think it's the simplest way of understanding automata. And then before doing NFAs and ENFAs, I'm going to look at partial and complete automata, what's the difference between them. And then I'm going to talk about why we don't really like NFAs and ENFAs. And we're going to look at how we can get these in ENFAs back to NFAs and NFAs to DFAs, which means we can always get to a DFA. And then finally, I'm going to end with the limitations of automata. Okay. So what's the problem? Wait, let me just make sure first. What are these slides? What do you mean? I made these last night. So in programming, there's two common types of problems that we run into sometimes, particularly containing like strings, and that's matching and finding problems. Matching problems is where we want to either accept or reject a string under some criteria, and finding problems is when, given a string and criteria, we want to find the start and end indexes of substrings within this big string that match the criteria. So here's some matching problems, and matching is what we're focusing on today, which would be, is a user input a valid postcode? Or is a inputted email valid? Or is a URL valid in a web application? I don't know if anyone else had any other examples of matching problems. Anyone else think of any? Yep, a Bitcoin address. So just a string, and we want to say, is it valid or not? When we learnt about this, we also looked at finding problems, but I don't think we looked too much further into them. But does anyone have any examples of a finding problem? So I didn't write any down here. But I think so. A finding problem could be given a long string of characters and there's a number within it. Where is this number? What is that number? So we want to find the starting index and the ending index, and then we can take out that substring. Okay, what is automata? And I'm going to introduce this through the concept of DFAs, because it's the simplest way to understand. So one potential solution to the matching problem, so we're looking at matching problems here, is using automata, which is represented using states and transitions. States are shown as circles, which have a unique label inside. The label can be anything, it's usually a number though. And usually we put states next to each other with increasing numbers like 1, 2, 3, because it's just easy to understand and talk about. Transitions are shown as arrows between these states with a character on them. So I'll show you an example. So automata would look something like this. So I'm not showing the start states or any of that. So we have three different states here and transitions here. But what do they actually do? So a state is... I'll see how I explain it here. So we consume each character in the input one at a time, transitioning between different states. When we're considering DFAs, we're only ever at one state at a time. And if after we've consumed the whole string, we happen to be in an accept state, denoted by the double ring of a state, we consider the string to be accepted. So if we were in state 1 here, and our string was AB, we're going to consume A, and by consuming A, we move to 2. Then by consuming B, because we're now on the second character, we move to 3. And if this was denoted by a double ring, that means AB is accepted. Does that all make sense? Does everyone understand this so far? Okay. Sorry, I don't know why I just took U as the whole thing. Okay. I'll just wait for SA dot. Okay. So one other thing we need to do is we need to define what state we start at. So in DFAs, there's only one, and this is done by pointing an arrow into a state, and therefore that's where we start before we even consume any characters. So it's important to define we start here. So now our string AB, before we've even consumed A or B, we're in 1. As soon as we consume A, we move to 2. As soon as we consume B, we move to 3. I think I talk about a bit more on this on the next slide. So we're starting off here looking at DFAs, and that stands for deterministic finite automata. The key word here is deterministic, meaning we only have one start state, and from any one state, we can only traverse to one other state with one input. And what I mean by that is, if we're at 1 and we consume A, we move to 2, guaranteed. If it wasn't deterministic, we could theoretically start at 1 and move to 2 or 3 after we consume A. But we're not allowed to do that in DFAs. And also, we only ever have one start state, which means we could only ever start at 1 here, or we could start at 3, but not both at the same time. Yep. It's very useful to think about DFAs, and they're easy to understand because we only ever start at one state and we're processing one character at a time, and we're only ever traversing from one state to another, which means we don't need to be worrying about being in multiple states all at the same time, because we can just think about it in a linear, I'm here, move to 2, move to 3, am I accepted or not? Yeah, so we just decide whether the string has been accepted based on just, do we end up in an accept state after consuming the whole string? Okay, I think I have a question next. So here, I've made a automata on the right, and I want to know which of the following strings are accepted. So we've got 1, 2, 3, and 4. So I'll just give you guys a minute to have a think. And also here at the top, I'm saying what the alphabet is, which is the characters we're allowed to consume at any point. And that's going to be important later when we consider incomplete or partial automata. I'll have a look. You say 2 and 4, Shay says 2 and 4. Yeah, you seem to be saying 2 and 4. Okay, let's have a look. So let's consider 1, ABA. So we would start at 1. So we're currently at 1, and we're just imagining we're at this one place. It's the only place we can be because we're doing DFAs. After consuming A, we end up at 2. After consuming B, we end up at 3. And we consume A, we end up at 4. Not a accept state. So ABA is rejected. For number 2, I'll go a little bit faster. But tell me if you want me to slow down. ABB, end up at 3, accepted. So yep, 2's right. 3 is BAAB. We end up at 4, rejected. We're finally 4, AAAB, accepted. Yep, so 2, 4 is correct. Nice. Okay, good job. So this is where it's important, where we define the alphabet was AB here. So a very common concept in automata is dead states, which is after a specific input, we travel to a state where we can never leave. So on the last slide, 4 is considered a dead state, as once we travel to it, there's no way to leave it. So we see here, if we're at 1 and we go to B, it doesn't matter what follows, we're always stuck in B. in a partial automata, we don't need to consider every input. So here, our alphabet is AB, and from any state, we're specifically defining what happens after we go to A, what happens after we go to B. And if you notice, we're never leaving out a specific input. And even the dead state, it has AB going in on itself. So the whole alphabet, once you're here, you're stuck. But in partial automata, you don't need to consider every input, and we simply ignore the transitions to the dead states and assume if you were at a state without a valid transition from our current state under the next character, we reject the string. So if we were at this one and we're at 1, let's say we just deleted 4 and we deleted B and A. If we're at 1 and we use a B, we just reject the string because we know it's never going to be accepted. Or if we go A, B, and then we do anything other than B, we don't say A goes to this dead state and then we continue processing. We simply just reject it right there. We reject the string rather than traveling to the dead state. Yeah. Later on, we don't usually define partial automata, or we don't say when it's partial automata. We usually just use partial automata, just because it's redundant, writing out this dead state and all the extra transitions. When, if we don't want a character to be allowed at this state, we just don't include it. So it's logically equivalent. It's simpler to write. However, if a question specifically says, I want a partial or non-partial automata, you need to make sure you consider it. Okay. NFAs. Is everyone good with the speed so far, or is there anything I've missed that, or you would want me to go more in on? Okay. Okay, so now we're going to consider NFAs. So NFA stands for non-deterministic automata. So we no longer have the constraint that there's only one start state, or the constraint that from one state with one specific input, let's say A, we're guaranteed to travel to only one of a state. So you can see in the example down here, we're still only starting at 1. However, after consuming A, we could be at 2, we could be at 3. So to be able to understand NFAs, you need to change your mindset. So I wrote here, to understand and evaluate whether a specific string is accepted now, we need to change our mindset of considering being at a specific state and always being in one state and following it, to rather being at multiple states. So in this example, we start at 1, but after consuming A, we could simultaneously travel from 2 to 3, so we need to keep track of being at 2 or 3. So here, if we're under the string AAB, we're going to need to start here. Sorry, let me make this bigger. I'm going to use my dog as like a marker of where we are. So our string is AAB. So we start here. We haven't consumed any of the string yet. So the first character is A. So after 1A, we could be here. We could also be here. So AAB. This is partial automata, so A doesn't come from here, so we can't, this one fails, so that's rejected. However, this one, we move to here, A. And then now we need to consume a B. B's not here, partial automata. We would have assumed it went to some dead state. So this is rejected. However, if let's say our string was AA, we would go here. This one would get rejected. We'd go here. Then we'd go here, and it would be accepted. And as long as we have one accept, the whole thing is accepted. Yep. Okay, I got another question. Which strings are accepted here? But now we've got, it's an NFA. I'll just give you a minute. Okay. Sherry says ABA and 4, so 3 and 4, 3, 4. You all seem to think 3 and 4. Okay, so let's check. Number 1. So 1 is AA. So we start here, we go A, and then we could also go here, so we could go. You see, it's always harder to think about this, especially when I'm trying to talk about it. But we could go to A, but then B would be rejected, so we could go here. We could go from 1 to 3, consume A, B, be rejected because we can't continue with that B. 2, so I think that's a similar story. A, B, A, rejected because we can't do the final A. 3 is A, B, that would be rejected, but we can go A, B, A. Oh, well, you can see my mouse. Just say if you can't, because I'm using it to show where I am. 4 is A, then that would be rejected, but we can go A, all these A's in the middle, it doesn't matter how many there is, and then it'd be accepted. And as long as there's that one accepted, the whole string is accepted. Finally, 5, there's no B's from the start state, so instantly rejected. Okay. So here I think I'm still talking about NFAs. Let me just put this back so I can see the title. Yeah, so we're still going on about NFAs here, but now we're looking at multiple start states. So here's an example where we want to accept either A followed by any amount of B's or B followed by any amount of A's. So this is one total automata, but they're not connected. So if we started here, we could go A, any amount of B's. If we started here, we could go B, then any amount of A's. So sometimes it might feel natural to be having multiple start states or being able to transition to multiple different states at the same times and stuff like that. But it's obviously harder to think about it because let's say we want to consider, is the string A, B accepted? We need to go to 1 and we'll say A, B. Okay, so it is accepted, and we know that from just considering the first one. If we wanted to check whether BA was accepted, we go to 1. B isn't a valid character at this state because it's a partial automata, so we just instantly reject it. So now we need to consider the other start state, so we could also be at 3 at the start. So then B, A, and then now we see we're accepted. So we only need that one example to show that the whole string is accepted. Nice. Okay, another question. I think this is the exact same automata, but I've just introduced a second start state now. And I think all of these strings are the same as well. So now which ones are accepted? Sorry, I'll move that. Also, what's something here, seeming as we're just building on the last ones, is there two strings here that we don't need to even consider and check whether they're valid or not? Let's see. 1, 3, and 4. Yep, we already know 3 and 4 are invalid because we demonstrated in the last one that we, even without this start state, we can accept it. So it's not going to make them invalid. We can always do that. Okay, SA says 1, 3, and 4. Does everyone agree? Okay, let's check. So they say AA is now accepted. So we could go A is rejected. Starting from 1, we could go A in itself, B, but then it's also rejected. So 1 isn't valid here. So actually, yeah, so not 1. So 1 isn't valid. We also need to check 2 and 5 though. So we know 3 and 4 are accepted. Does everyone understand why 3 and 4 are accepted based on our last one? Because we've already shown here, we decided 3 and 4 were correct. Oh, I just auto-corrected it. So we only need to check 2 and 5, yep. So let's check 2. A, B, B, A, A. So we could be looking at the start ones, but we already know it's not going to work. But we'll just check it anyway, just to show it. So we go A, B, 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 A, nowhere to go, and we're stuck. But we could have also gone down this path. A, B, nowhere to go. Okay, so 2 isn't accepted. So 3 and 4 we know are accepted based on they're accepted with just this input. So we just need to check 5 now. So if we start at 1, we can't go anywhere with B, so that's rejected straight away. But if we start at 2, we can go in on itself B, 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 A, and we end up in 4, which is an accept state. So it's 3, 4, and then also 5 now. Yep. Does everyone understand that, or do you want to look at another example? Or further on this one. Okay. I think now we're going on to epsilon NFAs. So I think epsilon NFAs are a harder concept to grasp compared to just normal NFAs. And the main concept is introducing epsilon transitions, which are optional transitions during processing, which don't consume a character. In an NFA, if there is multiple transitions of the same character from one state, we need to consider going down every transition. Oh yeah, sorry. So in an NFA, if there's 2 A paths coming off one state, we need to consider going down both of these. And epsilon NFA, although it can still have that, we also need to consider going down or neglecting to go down epsilon transition. So in this example on the right, we start at 0, and let's say our string is AA. We could, so after we consume A, we're going to 1. Our next character is going to be B, but we're not just at 1 anymore. We could also be at 2. So we need to go down every path, every epsilon path, and also consider being at that state. So after consuming A, I like to imagine it as we're not at 1, but we're at 1 and 2 simultaneously, because if we were at 1, we could also be at 2. So AA would be accepted as we could go A, epsilon A. So after consuming just our A, we're at 1 and 2 simultaneously, and then we can consider going down A. And then obviously 1 rejects that because it's B, and 2 accepts it because we go to 4. I don't know if I've explained that well, but I think it'll be good to look at another one. So if we start here, so let me do this here. So would the string AB be accepted here? I'll zoom in a bit. Would just AB be accepted? You know, I'm going to introduce that as well. Yep, because we could go A, we're at 2, but because we're at 2, we could also be at 3. So we're at 2 and 3 at the same time, pretty much. The next one is B. 2 would reject B, but 3 would let B go to 4. And there's no more characters to process, so we've finished now at 4. What about the string AAAB? So that's 3 A's followed by a B. Would that be accepted? Yep. So after consuming 1A, so we start at 1, we consume 1A, and we end up at 2. So now we've got AAB still to process. We can go AA here. So, sorry, I should have been more clever. So we're at 2 and 3. We can imagine it being at 2 and 3 simultaneously again. So if we were at 3 here, A would not be accepted because there's no A coming out of here, and partial automata again, we can just instantly reject it rather than having a fail state. But if we were at 2, we could go A in on itself again, and we're still at 2 and 3 simultaneously again. And then finally, we can use B would be rejected from 2, but 3 B would be accepted. And I also wanted to point out it's like a one-way thing. So considering when we're at 2, if we can be at 2, we can also be at 3. But just because we can be at 3 doesn't necessarily mean we can be at 2. I hope that's clear. Yeah, so the way I always think about it is if I can be in state 1 here, I could also theoretically be in state 2. So any input which I'm considering from state 1, I also need to apply to state 2. But it is the one way. Then we've got another question. So here we've got a more complex ENFA here. And which of the following strings are accepted? Fred says 1 and 2. SA says 1. Manj says 1 and 2. Shay says just 2. Okay, so we can already see it's harder to think about these when you're considering being in multiple places at the same time. So let's go through. So number 1, let's consider first. So we've only got one start state. So before consuming any character, we could only be in 1. So right now we can only be in 1. We just 1, no multiple states. After consuming A, where could we be? So starting at 1, consume A and we move to 2. So we're still only in 1 state at this current time, so it's decently easy. Oh no, we're not actually in 1 state, sorry. Because if we're in 2, if we're in 2, we could also be in 3, so we're simultaneously in both of these states at the same time. So we need to think for our next character. So we've consumed A, our next character is A again, we need to consider what would happen in 2 and 3. So if we're in 2, A would go in on itself, and then we'd still be in 2 and 3. If we're at 3, A would go in on itself, and we're just at 3. We're not at 2 and 2, because it's one way, yeah. So let's consider this current path of going 2 in on itself. So we consume A, and then we could move down and consume A again, and then B, and we'd get rejected. Yeah, it seems like it doesn't matter if we consume the A's here or here, we get rejected with just this B. Oh no, sorry, that's my bad. If we're at 5, we have an epsilon transition to 4, and if we ever have an epsilon transition to an accept state, that means we're also accepted. I don't know if I wrote this earlier, but if 5 isn't accepted, but it has an epsilon transition somewhere that is accepted, if we're at 5, we could also just be at 4, because it doesn't take anything to travel to 4. So 5 is also implicitly an accept state. So 1, we can say is accepting because A, B, we can go A, travel to 3, A, B, epsilon. Yep. Does that first one make accept for everyone? Not accepted. Yeah. I don't know if you can say accepted. Okay. Yeah. Acceptable, because it's only at least 1. Okay, so Fred says 1 and 2. Okay, I think people think it's 2 as well, but not 3. So let's consider 2. So we start at 1. We can only go down this one path to 3. We're still only at 3. We'll go A in on itself, B. So right now we're at 5 or 4, but we still have another character process. So if we're at 5, we can go A and be accepted. While at 4, it doesn't matter, but if we went A, it would be rejected, but it's acceptable, like Shay said, because there's at least one accepting thing. Yeah, so I think it's important, on what Shay said, when we're talking about DFAs, we talk about a string being accepted or rejected. When we're doing NFAs, we talk about being acceptable or rejected. Or unacceptable. Because an NFA just requires at least one of the paths to be valid. So it's not, we wouldn't say accepted, we'd say acceptable. Let's see. Just I'll explain manage. If you still want me to talk more about that, just say in the chat. Okay, so we've seen 2 is also accepted. So finally, let's consider 3. So we start at 1, we consume 1B. We're now only at 3. We consume a B again. And right now, we've consumed these first 2 Bs. We still have another B to consume. Right now, we're at 5. And because we're at 5, we're also at 4. But neither of these have a B coming out of it, so both get rejected. So it's not acceptable. Sorry, Okay, so as you can probably see, NFAs are kind of bad. And here's a few reasons which I want to highlight. They're harder to reason with. It's a lot harder to think about it. You're keeping track of where you are in multiple places. And it's significantly harder as a human compared to a DFA where you're only ever in one state at a time, which means you can just do it and keep track of where you are. That means there's a lot more chance for errors while doing this. It's also harder to implement for programmers for the same reason above, and it's also prone to errors. One of the more important ones is probably thinking about the runtime of an NFA. In a DFA, you're going to have to only process the C characters. So let's say if we have 5 characters and we have a DFA, sorry, ignore the transitions, but if we have a DFA and we go 1, 2, 3, we only have to do those 3 run times. I don't know like 3 steps on our DFA. However, in an NFA, we could be going down all sorts of paths and processing all different types of paths. So that's another thing which is bad about NFAs is I wouldn't say they're necessarily more inefficient because a DFA could be an equivalent DFA could be larger, but it's harder to reason with about their runtime. And of course, this becomes worse and worse as NFAs grow to anything more useful. So right now we're only considering A's and B's with epsilons. But if we think about like a real situation, so let's say considering the URL from our first example is a URL valid or not, it's going to become a lot more complicated. And if you wanted to use this for anything, like, I don't know, I don't think you would, but if you were doing like compiler design, it's going to be a lot more complicated. And imagine trying to think about in your head where all these paths are going. Yep. I don't know if anyone else had any other reasons, but these are just the few I came up with last night. If anyone else has any other reasons on why NFAs are bad. Or why they're, well, not necessarily bad, but more that you would want to avoid them. Okay. That's fine. I think these are the main ones. Oh, actually, one more I didn't talk about is also not necessarily runtime, but also storage and like memory usage. If you're only ever considering being at one state at a time, you can imagine a pointer pointing to this one state and it's moving to one state and it's always taking up the same kind of memory. In an NFA, it's going to be going to multiple states at the same time, which could have a lot more memory usage. Okay, so NFAs suck. So we want to get rid of NFAs, and we want to get rid of NFAs. And the way we do that is if we have any epsilon NFAs, we first convert those to NFAs. And then if we have any NFAs, we convert those to DFAs. And that means we can always get to a DFA. Because then if we have an epsilon NFA, we'll convert it to an NFA, then that NFA to a DFA. If we just have an NFA, we can just convert it straight to a DFA. So the first way we convert an ENFA to a NFA is like this. So this is the first one we have to do. Anything that points to a state that then later has an epsilon transition, which rather directly link to the extra state. What I mean by that is if we had 1 and 2. So, So imagine 1 connected to 2, which connected to 3. If we want to remove this epsilon transition, we need to think, so the way I've worded it here is, anything that points to a state that then later has an epsilon transition, we just rather directly link to the state it reaches. So 1 goes to 2 via A, and remember we thought if we're at 2, we're also at 3. So rather than going 1 to 2 epsilon, because 1 points to 2, which implicitly is also at 3, we just rather also do the A transition to 3. Does that make sense? So essentially, if we're pointing to something that then has an epsilon coming out of it, we just go, or multiple chains of epsilons coming out of it, we would just rather directly go straight to the states which the epsilons have. So I'll do another one. So even if we had 2 epsilons here, after consuming A, we could be at 2. Yeah. So after consuming A, we could be at 2, and if we're at 2, we could be at 3, and if we're at 3, we could be at 4. So rather than having these epsilon transitions, any way we could get to 2, we also just do straight to anything that transitions via an epsilon. Because 3 is connected via A now, and 4 is connected via A, and we've got rid of the epsilon transitions. Hope that makes sense. Just let me know if it doesn't. And also, finally, we need to consider also the accepting states. So let's say we come back to here. And like I said earlier, if let's say 4 is accepted, if we're at 2, we could theoretically, we're also at 3, pretty much. This is, I'm trying to be clear on how I'm talking about it. And the way I think about it is, if we're at 2, we could also be at 3. So anything at 2, we need to consider being at 3. If we're at 3, we could also be at 4. So if we're at 2, we could be at 3 or 4. So if 4 is accepted, 2 and 3 might as well also be accepted. And I wrote it here. 2 is implicitly accepting these ones. And then we remove these the same. And here just doing those 2 steps, we've converted this ENFA to an NFA. Does that make sense? So it's just the skipping the epsilon transitions by doing them directly, and then also turning any further along accepting states and making the kind of propagating through the acceptingness of that later state. Okay, the next step is NFAs to DFAs. And the way we do this is we're going to start, first of all, with just a DFA. And so we're going to start with a brand new DFA. And this first state is going to be a composite of the NFA's starting states. So if 1 and 2 were in the start states of the previous one, the NFA we're trying to convert, this new DFA would have the 1 start state as 1, 2. And now we need to consider where we could be for any input from either of these two states simultaneously. And we keep track of the name of this as curly brackets and all the different states we could be. And once we get to the end, we can rename them entirely, and the logic would still be the same. So let's convert this NFA together. Sorry, that's an ENFA. Okay. Let me just recreate this very quick. So this is a start state. 2, 3, 4, bum, 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 bum. Okay, so this is an NFA because 1 has 2 A's coming out of it, and it also has 2 inputs. We have an input at 1 and also an input at 2. So we need to think about how we would convert this to a DFA. Yeah, slow accepting. I think, yeah, that's how they worded it in the handout. So, yeah, so if 2 has an epsilon transition to 3, 2 is slowly accepting. Because if you were at 2, you could be at 3, so you're accepted. Okay, so the first thing is we'd create a composite state. So we're doing a brand new diagram completely. And we do a composite state between 2 and 1. So these are our starting ones. So if we start, we could be at 1 or 2, right? Yeah. And then we need to consider each input coming out of this state. Let's make it a starting state as well. So if we're at 1 or 2 and we have A coming out, where could we be? I don't know how you guys would think about it. 3 and 4, 2 and 3. So if we're at 1 and we have A coming out, where could we be? We could be at 2 or 3. But we're also simultaneously at 2. So if we have A coming out, we could also be at 4. So we could be at 2, 3, or 4 after this. Yeah. Let me just wait. You get that, Cat? I don't know why I'm calling you Cat. I don't know your name, but that's kind of weird for me to call you Cat. Cat hitting Jewel. Okay, so if we're at 1 or 2, and we consume A. Sorry, I just need to sneeze. Oh god, I just realised that's going to be in the recording. You can get it in the recording. So if we're at 1 or 2 and we consume A, we're going to be at 2, 3, or 4. Sorry. Okay. What about if we're at 1 or 2, so our start states, and we consume B, where could we be? What do you think for B? Two. So let's see. So if we're at 1 and we went down the B path, there's nowhere to go. This would be rejected, but not the whole string rejected because it's an NFA right now. If we're at 2 and we went to B, we can only go in on itself. So we've lost the 1 by going down this path. Yep. Okay, I'll go a bit faster through these ones. So if we're at 2, and so just 2 right now, and we go A, we can only go to 4. If we're at just 2 and we go B, we're only going on itself, so we can label it like that. You guys get what I'm doing here by saying where could we be at multiple times. 2, 4. Oh, okay, that's fine. So if we're only could be at 2 and we have B, we can only end up at 2. But if we're at multiple states and we have B, we can theoretically be in multiple places. 4 A to hell. 4 Yeah. We're doing a partial automata, so if we don't have a transition labeled, we just assume it goes to hell, or a reject state, or whatever. Okay, back to here. If we're at 2, 3, or 4, and we go A, where could we be? So we're at 2, 3, or 4 right now, simultaneously at 2, 3, and 4. And where could we end up? Via A. 2 or 4? Oh. I don't know if I just disappeared. Oh. 2, 3, 4, A to 3, 4, that's what it says. So let's check. If we're at 2 and we went A, we'd end up at 4. If we're at 3 and we went A, we'd end up at 3. If we're at 4, we can't go anywhere, so it's 3 and 4. So that's good job, Shay. Here, this is how I like to lay it out. I do all my A's going in one direction and B's going in another, because I think it's a lot easier to keep it maintained. This is what I did in the assessment, because we only had for 2 characters. So it's just a lot easier to keep it organized if I do it like this. Okay, 3 and 4. Oh, let's do B first. If we're at 2, 3, and 4, and we go B, where do we end up? So if we're at 2, B goes in on itself. If we're at 3, B goes to 4. And if we're at 4, we go nowhere. So we end up at 2 or 4. So I need to actually bring in a new state. 2 or 4. Let me know if I make a mistake as well, because it is very possible and likely. Okay. 2 and 4. Let's consider this now. This is what I said about this being neat and easy to maintain is kind of falling apart. But if we're at 2 and 4, and let's say we go A. So if we're at 2 and we go A, we get to 4. If we're at 4, we go to A, we don't go anywhere. So 2 and 4, it just directs to 4. So we can just say A goes to 4. We're not going to make a new state for 4 because it doesn't make sense to do it. It's representing the same thing. It's representing the old 4. Yep. Okay. We also need to consider B coming out of 2 and 4. So if we have B coming out of 2, it would go in on itself. 4 would reject, so 2 and 4, B goes directly to 2. Okay, so what haven't we considered? We haven't considered this path here. So what happens if we're at 3 and 4 and we go A? If we're at 3, we'd go A in on itself. If we're at 4, it'd be rejected. So 3, 4, and A just directs to 3. Yep. Sorry, that is meant to be an A. If we're at 3 and 4 and we go B, we just get directed to 4, which already exists down here. Let me just need to mess up a little bit. Okay. And then finally we need to consider A and B from 3. B goes into 4. Oop. Sorry, I don't know why I can't draw an arrow. There. B would go into 4. A goes into itself. Have I made any mistakes here? But I think this is the full thing. From every state, we've had A and B coming out of it, and we've correctly handled it. Looks good. Okay. And we can see we've got rid of these duplicate transitions. So A coming out of here, and we got rid of the multiple start states. So theoretically, you wouldn't do this in an exam, but these names, we've only used them to help us figure it out. But by changing all of these names, we're not changing the logic. But what we've done here is we've created a brand new DFA without all of these extra transition stuff, and these have identical logic. So we've made a DFA equivalent to our NFA here without, well, we've created with the same logic, but it's a DFA now. And we have a few more states, but it's just easier to think about it now. So if we went back to the question, which strings are accepted, I think 3 was accepted. Oh, yeah, there is one thing I've missed. Has anyone seen that? Yeah. We should choose which ones would be accepted. So I kind of messed that up. But it would have been anything that contained at least 1. So I can't remember what that was, but let's just say it was that. Like these, sorry. Let's say it was that. Sorry, I missed that. If this was 2, 4, we could be at 2, 4 at this point. So because 4 is accepted, it would be accepted. Sorry, I missed that. I hope that makes sense. Does everyone get that? As long as at least one of the states we're accepting, then the whole new state is accepting. Because it's all of these simultaneously. Yeah, so it was something like that. So in the old one, I don't know if this would work now. But let's say that isn't accepting, and that's 5. We could have gone here, A, or A, B, rejected. A, B, A. But here in this new one, we can just go A, B, A. And see that it's accepted. Like that. Okay. So that's NFAs to DFAs. And one thing I didn't do here is I didn't draw a transition table. So a lot of the time I was redoing the logic, and I was like, when I'm at 1 and I go A, where could I be? Or when I go... Sorry. Well, I was hoping to bring up my... my one in my assignment as an example of this. So if we're at state 1 and we go A, where do we end up? And I was rethinking about that logic all the time. But I think, was this assignment 1? Yeah, so this is what I did in my assignment, even though I got the question wrong. When I'm at 1, we go 2, 4. Sorry, if I'm at 1 and I have A, I could be at 2 or 4. If I'm at 1 and I went B, I could end up at 1. It gets a more complicated here, because if we look here, if I'm at 4 and I go A, I could be at 4, I could also be at 7, I could also be at 9. So rather than redoing this logic, let's say when I'm at 4, 6, 7, 8, 9, and I think, oh, where will I go if I'm A? I don't want to be seeing 4, what happens if I go A? 6 if I want to go A? 7, what happens if I go A? 8 if I want to go A? 9 if I want to go A? I don't want to be coming back to this and recalculating it every time, because I'm going to now reuse most of that here. So first of all, if I have the time, I draw this diagram here. And then now I can go 4. 4, I could be at 4, 7, or 9 if I go A. 6, I could be at 7, but that's already contained by the 4. 7, I can't go anywhere. 8, could be at 9. 9, I could be at 8. So A transitions to everything apart from 6. This is correct, but it was continuing on from something wrong. So yours might be different, but this bit is correct. So yeah, so it's just a lot easier to reason if you have the table, and you're a lot less likely to make mistakes. Okay. Convert this to DFA. I don't know if you guys want to do this, or if you want me to leave this and you can try it in your own time, because it's kind of hard to do a question like this because you're drawing. Do you want me to put this in the chat for after, if you guys want to have a go at it or not? Yeah, sure. And I'll make an answer for it as well. Okay. Finally, we get to the limitations of automata. And one of the main limitations are, by their name and their nature, they're finite. So, a DFA, deterministic finite automata, they're not infinite, so they can't... So there's some cases, like here, the bracket problem, we would require an infinite amount of states to be able to do the logic for an infinite amount of brackets. I can't remember what the word was for this. I don't know if anyone can say it in the chat. What the actual word was for what this is called. Yeah, irregular languages. Yeah. we can't represent irregular languages like this because they would require an infinite amount of states. So the bracket problem is an irregular language, so it can't be solved using automata. So they require infinite states, so sadly we can't do this with DFAs, so we're going to need something like CNF or another type of language to be able to represent this problem. I think that's it. I just put a picture of my dog here. And that's it. Does anyone have any other questions or anything in particular from over here that they would like me to go into more? Sorry. You're welcome, Shay. Okay, I don't think there's any further questions. You can always message me if you want to. I'll put this question in the chat, and I'll also put an answer in there. I just need to make the answer first. Okay, well, have a good day, everyone. Was later. Syntax of propositional logic with Shay. I'll be going to that. That sounds good. I need to revise the maths. Okay, no problem.